I believe you can see my screen right now. Is my screen clear?
Yes, I see it.
So let's go ahead. Is my voice clear?
Yes.
Ladies and gentlemen, I'd like to welcome you all to our today's extraordinary session. I am Al-Murtaza Ala Askar, you can call me Askar, and today's we're having Mr. Steven Rosenberg, no definition needed, a man with all the experience we wish to have in the future. To talk about him would consume a lot of time because the man's achievements are infinite, you can say. Mr. Steven, very happy that you're here with us today, and thank you for accepting our invitation.
Well, appreciate the invitation. I look forward to the presentation and the questions.
Thank you. About our drilling bootcamp, a complete guide for proficiency. Mr. Steven Rosenberg, an executive vice president and chief technology officer at Subsea Drive Corporation. More than 40 years of experience in the oil and gas industry, including 20 years operator and rig contractor drilling engineering positions. He is recognized as a global industry subject matter expert in casing and liner drilling operation and SPE distinguished lecturer. Would like to draw your attention, everyone, to our upcoming events. Geosteering by Dr. William Bill Donovan, registered professional engineer in Colorado, United States, president of Donovan Brothers. And we also like to draw your attention to the attendance registration for the 15th day. We'll send at the end of the session. Any questions that you have, you can drop at the chat box or raising hand button. I'd like it to be at the end of the lecture. Keep your mind with us and listen carefully. Mr. Steve Rosenberg, you can go ahead. The microphone is yours.
All right, thank you very much. Can you see my screen?
Loud and clear.
Great, great. All right. The topic of the lecture is liner drilling, a simple solution to complex drilling challenges. Why did I name it this title? Well, because as you'll see in the presentation, a single trip while liner drilling can mitigate hole problems in the well. All right, what are we going to talk about? We'll define liner drilling. Why would you ever want to drill with a liner? We'll talk about applications. When do you want to liner drill? Liner drilling systems. Right now, there's two types. There's a non-retrievable and a retrievable system. We'll talk about the differences. We'll talk about the engineering considerations. How do you design? What kind of factors do you take into account when you design a liner drilling system? We'll go over case histories and then summarize the lecture. What is liner drilling? The liner replaces the conventional BHA. It provides the hydraulic energy to the bit. It also provides the mechanical force to the bit. You'll see on this picture to the right here, we'll have a drillable casing bit, or it could be a conventional bit on the bottom of the liner assembly. We may have a stabilizer strategically placed above the bit for steering purposes, or actually if it's a non-retrievable system for passive directional control, giving it a build, drop, or hold angle. Above this, as we'll show in subsequent slides, we'll have the float collar and the liner drilling tools. The most important takeaway from this lecture, as you'll see, is the liner will drill and case the hole in a single trip. without having to trip out of the hole. So what are some of the liner system basics? A liner is a casing string with the top below the wellhead. You'll see in this schematic on the right here, how the liner, a drilling liner and a production liner shown in this schematic, the top does not extend to surface. Hence, it's called a liner, not a casing string. There's many designs to meet well demands. You can see here is a drilling liner. Basically, in this case, it's an extension of the surface casing. It can extend the fracture gradient to isolate drilling hazards in the hole, or else just to give you a better shoe to subsequently drill the hole. It can be set on bottom, or the liner can be hung off with a liner hanger assembly. Operators can set the liner on bottom if they so choose. If they don't want to run a hanger, as you'll see later on in the presentation, can decrease the hydraulic bypass area. So it could be advantageous to set the liner on bottom. It can be hung off with a liner hanger assembly. Probably 80–90% of the applications, operators will use a liner hanger, simply because if they do set a packer above it, it can withstand the forces when you mechanically set that packer. Liner can be cemented or uncemented. Sometimes an operator will drill a liner in from a high pressure to a low pressure or depleted zone, simply to provide a conduit into the low pressure zone where they can decrease the mud weight. What happens if you drill the liner, if you're drilling conventionally and you drill the liner, or you drill with the BHA from a high pressure to a low pressure zone, you're going to lose circulation. You won't be able to maintain the hydrostatic head, and the formation will collapse. Sometimes the operator will purposely drill the liner in from a high pressure to a low pressure zone to have the formation collapse. Knowingly it'll collapse, and then that could be in essence the cement job, providing the hydraulic isolation where you can safely decrease the mud weight and subsequently drill that low pressure zone. Liner drilling, a simple solution. It's very similar to conventional drilling methods in that the liner is the BHA. One of the big advantages of liner drilling is that there's no tripping. Many of your well control events happen while tripping. I think there's a stat that shows 70% of well control events happening while pulling pipe or in and out of the hole. You're only drilling the liner going south with the liner drilling, so to speak. So there's minimal surge swab effects. The success of liner drilling is determined by how the liner BHA and wellbore are managed. As I mentioned previously, you can design this liner BHA to maintain a build or maintain a neutral trajectory, or else a drop assembly, simply by strategically designing the placement of the stabilizers on that liner drilling system. For most part of this presentation, we'll be talking about a non-retrievable system, but we'll also mention the complexity of a retrievable system, and that's a liner system that can actually be steered. So why you want a liner drill? Obviously, you want to get the liner to your planned depth or total depth. You want to mitigate drilling hazards, such as losses. Many of you have probably heard of casing drilling, virtually identical to liner drilling, but in casing drilling, the top's extended to the surface. You mitigate losses, and because of something called the smearing or plastering effect. When you liner drill, for example, say you're drilling an 8.5-inch hole conventionally, typically 4.5, 5-inch drill pipe, you'll see you'll have a large annulus. But if you put a 7-inch or 7 5/8-inch casing in that 8.5-inch hole, you've severely decreased the annular space. So what happens while you're rotating this liner, you're plasticizing or smearing the cuttings. They're getting circulated up from the bit into that permeable formation, giving you, if you will, a perfect particle size distribution, as some industry experts like myself like to call it. And this is the mechanism by which you see reduced fluid losses in casing and liner drilling applications. Designing a casing and liner drilling job, you typically want to have a casing OD to hole size ratio greater than 0.8. This gives you, as proven in many applications, a better chance of getting that smearing effect where you do see reduced losses as compared to conventional drilling applications. Now, where you don't see the reduced losses is if you're drilling vulgular limestone or highly permeable, and I'm talking about greater than 1 to 2,000 millidarcy or 2 darcy formations. You're still going to lose circulation in casing and liner drilling. But the big advantage, like I mentioned, due to the close proximity of the liner to the wellbore, is that you can maintain, in many instances, the rate of fluid loss on the backside with a dedicated annular pump or perhaps a trip tag pump. And because operators lose fluid on the backside in lost circulation scenarios, that's the mechanism by which they get stuck. So if you can keep up with the fluid losses on the backside because you've got a narrow annular geometry with a dedicated pump, that's a big mitigant to stuck pipe. Wellbore instability. Many times operators have difficulty getting casing to bottom. In some instances, if you have the hole already drilled, the operator can put a reamable or drillable casing bit on the bottom of that liner to rotate the casing to bottom. But sometimes if they don't have this bit on the bottom and they've tripped out of the hole with high overpull, they may not be able to get the casing bit to bottom in a conventional application where they might have a casing shoe on the bottom with no cutting structure. So by drilling a liner in, you don't have to fight the wellbore stability, which sometimes precludes you from getting casing or liner to bottom. Depleted zones, a great application for liner drilling. If you know you have a depleted zone, you could potentially space out the liner drilling system so to minimize connections across that depleted zone to get your liner to bottom. The problem with making connections in a depleted zone is that you stop pumping, you stop rotating, and you can get what's called differentially stuck. But by maintaining rotation and drilling and circulating, that's a big mitigant for mitigating depleted zones. Now, sometimes you'll have an advantage of liner drilling is you could potentially get a 130-foot stand in there. But if your depleted zones, you have two of them, say they're spaced out a couple of 100 feet apart, what you need to do is talk to the rig contractor and see if they can actually make what's called a rotating connection. In other words, have the rotary table rotate independently from the top drive while they're making the connection. And this way you can mitigate differential sticking to the wellbore. Now, in some instances, that can't happen because the rig is not designed. So what you may consider doing is put a continuous circulating system on the rig to maintain circulation while you're making the connection. Pressure transition intervals. I mentioned this early in the presentation. Sometimes the operators want to go from a high pressure to a low pressure zone, and you can't do it with conventional methods. So what they'll do is pick up a drilling liner or drilling casing string, knowing they will be stuck in that lower pressure zone, and drill that liner until they get stuck. Now you've got isolation due to the formation collapsing around the pipe, where you can drill that lower pressure zone, which has been isolated from that higher pressure zone above. I hope you all have some questions on this after the presentation. You keep every foot drilled. You don't have to pull the liner out of the hole. No rig modifications. I'll spend a little time on this. When you go out to for a liner drilling job, really, like I say, the liner is the BHA, as in conventional BHA applications. You don't have to redesign the rig or reconfigure the rig. You basically are ready to go ahead and drill the liner in. No rig modifications. This is a big deal. In managed pressure drilling, I know they have to go out to rigs and pre-do the pumping, the piping and instrumentation prior to the operation. In casing and liner drilling, you've got your top drive, you're ready to drill the liner in the hole. And last but not least is our key takeaway message: one trip to drill and case the well. Let's talk about non-retrievable systems. These are the simplest and most common. As you can see, you have a casing bit on bottom, and this can be a designed drillable casing bit where you can drill through. You'll have a stabilizer or several stabilizers above the bit, depending on what you want to do, what kind of trajectory you want to maintain. And then you'll run at least one, possibly 2 or 3 float collars on a liner drilling design. And you'll ask, why do you want to run several float collars on there? Well, because you're going to be circulating for a long period of time, and you want to have redundancy with those float collars. On a simple liner installation, you can probably get away with 1 float collar, because you're not going to be circulating that much unless you've got some hole problems where you have to wash and ream that liner to bottom. You run centralizers as per your cementing design, and you can run an annular casing packer if needed for isolation. And then you have your liner hanger packer assembly above. Big advantage of the non-retrievable liner systems over the retrievable systems, which we'll talk about in the next slide, is you've got the ability to cement this liner in place prior to, without having to pull the assembly out of the hole. Basically, you're going to be pumping cement down the liner through the bit, which has nozzles, and your cement will be circulating up just like you would in a conventional liner installation job. Disadvantage of a non-retrievable liner system: you have the inability to actively change direction. I mentioned previously, you can maintain the trajectory, but you can't turn the well or purposely build angle. You have to, you do not have that ability to change direction. And you can only run cased hole logs. Why is that? Because you're casing the well, or in this case, lining the well as you're drilling the liner in. So you're limited to cased hole logs. Now let's talk about the more complex retrievable liner systems. I've got this schematic courtesy of Baker Hughes. Basically, the big advantage is you can actually steer the liner. Let's go over some of the components. You've got a casing bit on bottom. For example, if this is a 9 5/8 inch liner, you're going to probably have an 8.5 inch pilot bit on the bottom. You'll have the BHA with your directional tools, your LWD if you want a log wall drilling, and MWD for directional purposes. On the bottom of the liner shoe right here, you're going to have a reaming bit. So you've got to have a 12 inch or 12 1/4 inch reaming bit to allow passage of that 9 5/8 inch liner to enable that to be drilled in the hole. You've got a locking mechanism which locks in this pilot BHA bottom hole assembly in place. And then you've got your inner string and your setting tools up above. You can log while drilling. LWD, logging tools can be positioned in this pilot BHA. Multiple trip capability. What happens if this 8.5-inch bit gets damaged while you're drilling? Well, you do have the potential of pulling this BHA out of hole and rerunning another bit. Or if the pilot BHA, if one of the components fails, you can pull this BHA out of the hole and rerun it in. However, there is some significant risk for this. The liner will be exposed to open hole. Bad things can happen if you can't circulate or you have a unstable formation. So you really have to be careful when you run this system. Also, when you reach TD, you've got to pull this BHA out of the hole prior to cementing. Unlike the non-retrievable systems, the retrievable systems require a trip prior to cementing. That's time, that's money, and you're probably not going to get as good a cement job with a retrievable system as you would in the previously discussed non-retrievable system. Probably the most important thing in liner drilling design is the connection. Those are going to be exposed to the most torque. Connections should be proven in liner drilling or casing drilling applications. In other words, if you guys see an application for casing or liner drilling, make sure the connections you've used have been successfully used in proven liner or casing drilling applications, or talk with the connection vendor and make sure they've done their homework regarding finite element analysis and how many cycles or rotations to failure based on your directional or tortuosity of the well. The connection should have high resistance to compression, bending, and tensile loads, obviously, because you're going to be drilling this liner in. It's going to be exposed to the same forces as if you've drilled in with a conventional BHA. Very important here, high resistance to cyclic fatigue. As I mentioned, you could be rotating for 4, 5, up to maybe even 50 hours. There's a term called K-revs, thousands of revolutions. Once you get up above 25 to 50,000 revolutions, you could become exposed to cyclic fatigue, especially when you've got dogleg severities greater than 3 degrees per 100 feet. There you want to talk to your connection vendor, make sure the casing has been rotated in a similar dogleg environment, or the vendor has done significant testing to prove that it's resistance to the cyclic fatigue based on the dogleg that you'll be drilling this liner through. Obviously, you've got need high torsional resistance because you're rotating the liner. There'll be economic considerations. Do you want to use a premium connection, or do you want to use something similar to buttress? You got to take that into account. And last but not least, you want to you want to ensure connection integrity on the rig floor. All this is for naught if you don't make up the connection properly on the rig floor. Okay, liner drilling systems, design considerations. Are you going to be directional drilling? Do you need a hanger or a packer? As I mentioned previously, a hanger and a packer decrease your hydraulic bypass area, which increases the equivalent circulating density, increasing your propensity to possibly pack off or get stuck. So you've got to take that into consideration. How will these affect the liner drilling application? Bypass area, setting sequence. Do you want to set the liner running tool prior to cementing or after cementing? There's advantages and disadvantages to both, but most of the advantages come when you set the liner prior to cementing. Is a hanger necessary? Let's talk about float equipment. As I mentioned, you want multiple valves or multiple float collars. Here's a schematic to the right where you've got a poppet valve configuration and a flapper valve configuration. In casing and liner drilling applications, the poppet valve is preferred. Why do I say this? Because if you run autofill or flapper type, especially running a flapper in the closed position, it's exposed to a lot of circulating hours, and this flapper, if it flaps enough, it could potentially break off and plug off your circulation path, and then you'll have to pull it out of the hole. If you do drill with a liner and you need autofill equipment, I recommend running it in the open position while you're drilling. Also, for spacing, your shoe track requirement for cementing will dictate the spacing. In other words, how much contaminated cement do you want to hold in your shoe track will determine the spacing. The spacing itself for the float collars will not impact the liner drilling operation. So if you need an 80-foot shoe track, that's fine. If you need a 120-foot shoe track, that's fine. Not going to impact the liner drilling operation. It's all a function of your cementing requirements. Centralizers and stabilizers. I get asked a lot about the design for these things. You do want to run solid body centralizers, preferably with non-welded blades. This picture I'm pointing to right here is a Weatherford centralizer designed for casing drilling. Basically, it's solid body. The blades are integral to the body. In other words, this is one-piece cast steel. On the bottom of the centralizers, you'll see these small ports. That allows for some circulation inside the centralizer to remove cuttings and debris, to allow this centralizer to become a non-rotating centralizer. In other words, rotating independently of the formation. So it basically slides down the casing itself rather than rotates with the casing, which decreases torque in the long run. As you'll see inside, there's a rubber lining, and this will decrease the friction between the casing and the centralizer, decreasing the coefficient of friction, reducing the torque during the rotating operation. Another type of centralizer, it's called a thermally spray centralizer. I think Innovex has these. It's a WearSox design. Basically, the centralizer is sprayed onto the casing or liner itself. Advantage of this is especially in tight clearance situations. For example, if you're running or drilling in a 9 5/8" liner in an 8.5" hole, and you run one of these where the body encompasses most of the flow area, you've severely restricted your hydraulic bypass, increasing the propensity for pack-off events. But you can see they actually spray the blades on this piece of pipe, and there's no body. So it maximizes that pass-through or hydraulic bypass area for circulating cuttings and circulation path, which will decrease your chances of a pack-off event. Also want to consider high-performance stop collars. Ace Oil Tools has a ratchet-type stop collar that's good for 90,000 plus pounds of holding force. The last thing you want is a centralizer to slide down the pipe. That would cause you to have a bad day when you're liner drilling. Drilling fluid and cementing design. If you do plan to pump lost circulation material while you're drilling a liner in, and you're pumping greater than 25, 30 pounds per barrel with a lot of fibrous material, you do want to have that lost circulation vendor do previous testing in a controlled environment to make sure that material does not plug off your liner equipment or your casing bit. You always want to keep a low amount, probably less than 5 pounds per barrel of fibrous material, because fibrous material has a high propensity for plugging off. But really question the vendor if you have to use a lot of lost circulation material, because this could defeat the whole purpose of liner drilling. Because remember what I said, because of the narrow proximity of that liner to the wellbore, that's what gives you the best chance for mitigating lost circulation and reducing losses. So be real careful with the type and the amount of lost circulation you pump. Cement and wiper plug system, based on your cementing design, you should be able to run a single or a dual wiper plug system. This should not influence the liner drilling operation. Single or multi-stage cementing tools are compatible with liner drilling, and there's mechanical or RFID, remote frequency ID enabled intervention. Why did I bring up RFID enabled intervention? Say you've got a stage tool located in a weak fracture gradient environment, where you can open up these tools with a simple pressure pulse or a tag, which will reduce the pressure surge from opening that tool on the formation. Now we'll talk about what kind of bits do you use for liner drilling and casing drilling. I'll show you 2 bits right here. The bit on the left, this is a Weatherford design. It has an aluminum nose. It's got PDC cutters mounted on a thin steel rail. The aluminum, this is all one piece aluminum stick up right here, and the thin steel rail is mechanically locked into this piece of aluminum that's sticking up part of this nose right here. You have copper, in this case, ceramic nozzles. Ceramic nozzles are good to about 400 feet per second nozzle velocity. Copper nozzles, about 100 feet per second. In drilling applications, we recommend, if you do use this bit, ceramic nozzles. It gives you more versatility with pump rates, so you won't have erosion to wash out this cavity right here. The big advantage of this Weatherford design, because of the aluminum nose right here, it's got 85% less steel than, say, a Baker Easy Case bit, which is made of aluminum alloy steel, which makes this bit a lot easier to drill out. So you do want to have a bit that reduces drill out time, particularly in deep water or high spread rate, rig spread rate applications. 1 or 2 hours makes a big difference. Now, comparing the Baker bit right here, this is an aluminum alloy steel design, PDC cutters. You've got tungsten carbide nozzles. Very good design. The major difference is the nose here is steel. The nose here is aluminum. It's going to require a special type of bit, PDC bit, to drill it out. That bit may or may not be properly designed for the subsequent hole that it's going to drill. Where in this case, you can drill out with any PDC bit. Does not require any a special design to drill out. So each bit has its own pluses and minuses. Another big advantage of the Baker bit, it does have a bypass port. Say the nozzles get plugged off, a certain amount of pressure will open the bypass port located on the side of the bit, so you can continue your cement job in case these ports are plugged. Cement is pumped through these nozzles right here. So you have to liaise or talk with the cementing vendor to make sure the cement you are pumping through here is okay for the nozzles. In other words, you've got enough flow area, enough nozzle area that you won't dehydrate the cement while you're pumping. And really, there's been no instances of that happening in casing drilling operations. It's just a good question to ask the cementing vendor. Now, designing of the cutters, you want to look at the formation you're drilling through. Typically, casing drilling, if you run a sonic log, anything greater than 65 microseconds per foot, which is approximately 15 to 20,000 PSI unconfined compressive strength, that could be a potential application. Once you start getting less than 65 microseconds per foot, the formation becomes too hard and you're going to be drilling so slow, and you'll require multiple blades on here, really complex design, and it just may not be an application for casing drilling unless it's for a short interval. Most casing and liner drilling is done for limited intervals to mitigate a problem. Other applications, for example, offshore in the Asia Pacific region, they may drill in surface casing just because it's cheaper to drill in the surface casing than it is to drill that surface casing pilot hole and then run the casing. So that's for drilling optimization. You may not even have to have a problem, and that could be an application. So if you got rig spread rates over $200,000, $300,000 a day, well, yeah, it's cheaper to drill in the casing rather than drill that pilot hole and then run the casing. Density logs can be used to determine the application. Greater than 2.5 grams per cubic centimeter on a density log typically is getting out of the realm for casing drilling, a little bit hard. Not saying it can't be done, but you really got to look at the application to see how far you need to drill, because the bit could wear out early. The last thing you want is the bit to wear out early and either not get your casing deep enough or have to pull it out of the hole. Okay, I put together a little liner drilling engineering matrix slide right here. On the left, you'll see liner design and operations parameter. On the right, you'll see hydraulic loading, all the engineering design constraints. So basically, your liner design, your operating properties, operating parameters, pipe properties, connection design, and setting system, it's all got to be compatible with the mechanical loading, torque and drag, helical buckling, and cyclic stress fatigue. All this has to match up. Your operating parameters, such as weight on bit, revolutions per minute, flow rate, standpipe pressure, it's all got to be within these design constraints. You're going to run a torque and drag model to make sure you're within the torsional limits. You want to make sure you're not helically buckling the pipe. You don't stack down too much weight on bit where the pipe goes into helical buckling. We mentioned cyclic stress fatigue. How many cycles or rotations based on the dog leg that the liner will be exposed to. I find the best vendor for determining cyclic stress fatigue in a liner drilling application is Tenaris. Not promoting Tenaris, but they do have a very good program to take into account how long that liner is drilling and will it or will it not prematurely fatigue the connections. All right, probably the most important this is case histories. Where has the applications occurred where we've solved the problems? Here's an application from High Island in the Gulf of Mexico shelf. They had a 7 5/8 inch liner installed about 13,685 foot measure depth. Immediately below it was a 17-pound shale and a 2 pound per gallon equivalent sand. So the objective was to drill the liner through this 17-pound shale and 2 pound per gallon sand in a single trip. Well, previously they got conventional BHA stuck in this depleted sand, and after 24 hours, they managed to pull it out of the hole. So what were the objectives? To isolate the 17-pound shale and sand. Conventional methods, as I mentioned, resulted in stuck pipe. They wanted to exceed the 6.5 inch hole conventional drilling limits. So about 830 feet of a 5.5 23-pound liner reamed and successfully drilled 113 feet of hole. isolated the 2-pound sand and the 17-pound shale on a single trip and saved the planned 3.5-inch completion. Now, while drilling the liner, and I was actually on this job, circulation was not lost, maintained continuous circulation, and got a satisfactory cement job. The hardest part of designing this application was actually figuring out what mud weight to use. You didn't want to run a 17-pound mud weight because you had that 2-pound sand below. And what's going to happen to that 2-pound sand? You're going to fracture, and you're going to fracture the formation and lose circulation, potentially stuck to pipe. So we decided on a 12-pound system, water-based system. And by using the geometry of the 5.5 by 7 5/8 inch liner, we managed to fight off that 17-pound shale and no lost circulation, and drilled an extra 13 feet into that sand and got a good cement job, and we're able to save that 3.5 completion. And then another application in the Mississippi Canyon, Gulf of Mexico. This was in fact a BP job. They had 13 5/8 by 14-inch casing, set at about 12,900 foot measured depth. But they knew they had a depleted sand, a 60-foot sand, about a few hundred feet below this shoe right here. And they had to mitigate this in a single trip. So what they decided to do was drill a 9 7/8 62-pound liner using liner drilling principles through this depleted sand. Sand had a 6.5 pound per gallon pour pressure, about 2,500 millidarcies in permeability. We knew we were going to get complete losses while drilling this sand. So at the end of the game, the 9 7/8 inch liner drilled about 300 feet. Total losses on this case. But while drilling this sand, you could actually see a reduction of losses. They were losing, I think it was 330 gallons a minute prior to, or barrels per minute, prior to the encountering the sand. While they were drilling this sand, the rate of fluid loss dropped to under 300 barrels per minute. And then gradually it increased again to the 330. What this showed is you were getting some smearing effect across this sand. This could not have been done with conventional methods. The annulus was kept full. What did I mention previously? In high permeability vulgular type formations, because of the narrow annulus, in this case, a 9 7/8 inch casing, we drilled a 12-inch hole. Annulus kept full via a dedicated pump. The depleted sand was isolated. A 37-degree inclination was maintained over 306-foot interval. What I failed to mention earlier is that liner drilling, you have stiff assemblies. You can typically maintain that tangential angle that you had built. For example, in this case, it was a 37-degree angle. You've got a stiff assembly, very similar to a stiff or a packed hole, bottom hole assembly you would use in conventional drilling applications. Here's an application in Romania. There was an 8-meter salt section right here they had to isolate. The problem was they couldn't get a 7-inch liner through this salt because it kept collapsing on them. So the objective was to isolate the 8-meter salt creep with the liner. Salt movement prevented the liner installation. They had 3 sidetracks prior to deciding on liner drilling. What's the definition of insanity? Doing the same thing over and over again and expecting a different result. Well, it took them 3 tries, but they finally decided to liner drilling, and that was the solution. About 1,100 foot of a 7-inch, 26-pound liner drilled 17 meters through the salt and the claystone. The salt section was isolated with a 7-inch liner. Successful job. Offshore Indonesia, operator had 9 5/8 inch casing, set at 84, 87 feet, measured depth, 67-degree hole, They had a couple of sidetracks when they tried to drill conventionally through this sand, shale, and fractured limestone. What happened when they got in this fractured limestone? Formation collapsed because of lost circulation, had to pull it out of the hole. Decided to try a liner drilling, a 7-inch liner. They wanted to isolate this loss interval with the liner. Conventional methods resulted in 2 sidetracks. The 7-inch, 26-pound liner drilled in about 350 feet, all the while with total losses because you had this fractured limestone, very high permeability. But they were able to keep up with the losses, which was estimated at 20 barrels per hour, with a dedicated trip tank pump. That's why they never stuck the pipe while drilling the liner in. They were able to keep the 7-inch, it was about a 2,000-foot liner, annulus full, maintain that 67-degree inclination. Similar application in offshore Mexico in the Gulf of Mexico. The operator had, this was a Pemex job. The operator had 13 3/8 casing set about 5,700 feet measured depth. Several attempts were made to drill through this unstable shale and fractured limestone in a single trip. What the objective was to get a casing seat right below this unstable shale so they could drill into this fractured limestone with a decreased mud weight. They were using, I believe it was 15 pound per gallon mud. So they wanted to isolate the shale with a 9 5/8 liner. Multiple stuck pipe events occurred. The 9 5/8 53-pound liner, it was actually a 5,000-foot 9 5/8 liner, drilled in 266 feet without losses. The beauty of the liner drilling application was they had a geologist on location. So once they got to the bottom of this shale and tagged the cap rock of this fractured limestone, they had a beautiful casing seat. Never got into that limestone. So they cemented it with no circulation, and they were able to set their 7-inch casing through that with no further difficulties. Maintain a 75-degree inclination over that 266 feet of liner drilling. And the last example I have right here is another Gulf of Mexico application where an operator had 13 3/8 casing and 1,530 feet, but they had a catastrophic loss zone below this 13 3/8 casing and 9 5/8 right there. So the objective was to isolate a catastrophic mud loss interval with a 7-inch 23-pound liner. The conventional methods resulted in 2 sidetracks. They tried to drill through this loss zone with conventional methods. The 9 5/8 casing they had set at 7 and 5 at the 4150 to top set this shoe, this interval right here. They drilled a 7-inch 23-pound liner, about 800 foot in length, 500 feet with total losses. But again, they were able to keep the annulus full because of the close proximity of the 7-inch liner to the 8.5-inch hole with a dedicated trip tank pump. They obtained the required 11.5 pound per gallon formation integrity test. Successful well. Again, they tried multiple sidetracks, expecting that to work in a conventional application. So what are the key takeaways? Drilling hazards can be mitigated in a single trip. There's no rig modifications. As I mentioned, you can go out to the rig with this liner drilling, same as if it's a conventional liner drilling installation, and drill the liner in place without having to modify the rig. Losses are more manageable than with conventional drilling, and one trip to case and drill the hole. And with that, that concludes my presentation. Appreciate your attendance, and I'd be more than happy to entertain questions.
Hello, Mr. Steve. This is Yusuf. I believe
Steve.
Hello.
four questions for you. And the first one is that you mentioned the plastering effect, and basically it's how the liner drilling push the cutting into the formation and
Right.
okay, and thinning the mud cake, I believe. So how can we optimize the plastering effect that you mentioned?
The question, how do we optimize what now?
The plastering effects.
Ah,
that you
okay.
mentioned.
As I mentioned, you want to design liner drilling to have a casing outside diameter to hole diameter ratio of greater than 0.8. So the higher that ratio it is, the more smear effect or plaster effect you'll get for the cuttings into the wellbore. So for example, a 9 5/8 and a 12 1/4 will give you something about 0.8, 0.82 ratio, which is a good design. Many 9 5/8 applications now use a 12-inch bit. So yeah, the closer you can get to a value greater than 0.8 casing. Does that answer the question?
But was just have another question regarding
Sure,
this point.
sure.
Is there a motion with the small annulus space does not crush the well of the well?
Does not
like frackage.
What's your question? Does not are you talking about pack off the well? I didn't understand the question.
No. We have a small annulus space, and we are the liner is rotating. So is the rotation crush the wall of the well?
Yeah, are you worried about fracturing the well?
No. I like the collision of the liner drilling with the wall of the well. So
yeah, the liner,
the rotation of the drilling line.
Yeah, if you can visualize that, the cuttings getting circulating up by the bit and the liner rotating, that's going to crush the particles, and the side forces, the eccentricity of the liner created by the rotation is going to crush those cuttings and force them into the permeable parts of the formation. And that's what's going to give you a strong filter or mud cake and decrease the losses as compared to conventional drilling applications.
Yeah, I see. My second question is just regarding to the pressure transition interval that you mentioned.
Mm-hmm.
So what is the advantage over conventional BHA, and how can we isolate the depleted zone without facing collapse or washouts?
Yeah. Okay. With a conventional BHA, say you're drilling from a 14-pound shale environment and you get into a depleted area, say 2 pounds per gallon immediately below that. What's going to happen with that conventional BHA with that 14 or 15-pound mud once you get in a 2-pound environment? Well, the mud's going to leak off into the formation, and that unstable shale above it is going to collapse on the pipe, and you'll be working with a sidetrack. You'll have a sidetrack situation. What I'm saying is, knowing you're going to get stuck, drill with a liner through, even with that 14-pound mud. You may get 20 feet, 30 feet into that depleted sand. Yes, the pipe is going to become stuck, but now you've got your design pipe into that depleted sand, which will enable you to decrease that mud weight from, say, 14-pound down to seawater, which you might want in an offshore application or a low weight fluid. And you won't have to sidetrack the well. big advantage right there. It kind of sounds counterintuitive, but really it's not. It makes a whole lot of sense. So if it's almost like putting a straw in the well. Now you've isolated that straw and you can decrease that mud weight to enable you to drill that lower pressure formation because you're isolated from that higher pressure formation on top. Make sense?
Yeah, I see. Then
There's
my
some, I tell you what, if you've got
Go ahead, go
more
ahead.
questions related, send me an email and I can send you some papers which talk about that drilling. You'll get a
that
really
would be
good
great.
understanding.
Yeah,
Yeah.
that would be great. So my last question about the packer and hanger. So why they increase the equivalent circulating density? That
Great question. Great question. Okay. Because the hanger and the packer, I'll give you an example, a 9 5/8 inch liner hanger system. The hanger may have an OD of like 12 inches, 11 3/4, 12 inches. And what's the ID of that hole? That's going to be about 12 1/4. So you've got a minimal, a greater restriction right there. Also, the packer could be a little greater than 12 inches. It could be 12.1 inches in a 12 1/4 inch hole, which further reduces your and increases your restriction in that area, which will, when you're circulating, increase your equivalent circulating density. And depending on your pore pressure frac gradient profile, that may be enough based on your circulating rates to pack off or potentially fracture your formation. So does that make sense? Yeah.
Clear.
Any further questions?
For me, no.
Any further questions? Sorry?
That's my last question, but I believe there's some question in the chat box.
Dear attendances, if any questions you have, you can type it just below in the chat. Here is a question from Mr. Nasser. While drilling liner casing, what happens with stuck? How can we free the pipe?
I love, that's a great question. I really like that question. Well, because we typically don't run drilling jars on a liner drilling application. And the reason we don't run the jars is because we really don't know where the stuck point's going to be. You're typically done. You're not going to free it. I say that, and that has to be part of the management discussion prior to the liner drilling job. What is the minimum acceptable depth you want to drill that liner to? Say, for example, ideally you want to drill the liner to 5,000 feet to get to a planned TD. But in reality, you're drilling hazard zones at 4,800 feet. And once you get to 4,800 feet, that's a success too. So what I always, when I used to run these jobs, I would always ask the operator, what is your minimum acceptable depth if we start packing off or start having drilling problems? And typically it's to get below that last hazard zone. So once we get below that 4,800 foot, as I just mentioned, if we do start packing off, we're not going to start picking up the pipe and potentially reducing the hole that we had cased off to work the pipe. We're going to call it good right there. Does that make sense? So plan for not being able to free yourself if you do get in a stuck situation. I have been involved with a couple of liner drilling applications where after 24 hours of circulating, they did get free, but that's a rare instance. Liner drilling is like anything else. You can stick the pipe, although there's a less chance because you are drilling a better well bore than you would with a conventional BHA. Does that make sense?
Thank you, Mr. Steve.
Yep. My pleasure.
I guess that's enough for today. Thank you, Mr. Steve, for bearing with us, and we shall have you in further sessions.
I appreciate it. And you guys and girls, feel free to email me with any more questions. I really believe in liner and casing drilling. You've got my email, and I will send you related papers and other things I've been associated with liner drilling to show how it is a simple solution to complex drilling challenges. But I appreciate your questions, and really enjoyed talking to you.
Yeah, very, very grateful, Mr. Steve. Thank you for today's session, and we shall see you in some future sessions with more extraordinary knowledge like this one. I would like to take benefit of it, and thank you. I'm glad that you accepted the invitation.
All right, my pleasure. My pleasure.
Thank you, Mr. Steve.
All right, you guys have a good rest of your evening.
Thank you.
All right, bye-bye.
Bye-bye. Dear attendances, would like to draw your attention that you have to fill the registration form right below in the chat, where you can find the link, or you can find it in the group of the bootcamp. I'm very glad to have you here today, and see you some other time. Just remember to fill the attendance form. السادة الحضور، يرجى منكم ملء استمارة الحضور اللي موجودة أسفل بالشات. شكرا لكم على حضوركم، إن شاء الله نشوفكم بأوقات قادمة. شكرا.